So we're going to talk about escaping from model land. So John described quite nicely there some of the issues that we have when we are making a model or a simulation, and we treat that as the world in itself. We fail to make that distinction between the model world and the real world. The model world being this elaborate mathematical or conceptual sphere of something that we are interested in modelling. But if we fail, as you said, to take that jump back from model land into the real world, then we're not producing anything that has any direct relevance for the kinds of decisions that people might wish to take. So I'm a physicist by background. I've worked in climate science, so my kind of reference point for model land is the land of climate models. And those are quite nice because they look very much like the real world, but often shown in pretty colours like these. Now, I guess the question is, what does, if we are working in model land, we can come up with a completely self-consistent, internally coherent theory of how everything works. Within model land, as John said, every uncertainty is resolvable. That'd be right. We can assign a probability to any event in model land, but perhaps if we're interested in the probability of, say that we follow some emissions trajectory over the 21st century, we're interested in the probability of a certain amount of temperature rise, or we're interested in the probability of a certain impact happening in Warwick in 2100, then maybe we take lots of models and we look at them all and we construct a probability distribution over those models, but that's still a probability in model land, not a real world probability. Now, in model land, sorry, I've just realised I don't have a timer anywhere. Will you tell me when there's 5 left?
Yes, I will.
Yeah. While we are in model land, what are the problems that we might encounter? This is a Hawkmoth. How many of you have heard of the butterfly effect? Quite a lot. Great. So chaos was fashionable a few years ago. Everybody's heard of the butterfly effect. It's this idea that if you were to go back many years and tread on a butterfly in 1950, say, then that would cause some dramatic implications for the future. That essentially it's a statement of dynamical instability. What you're saying is, if you have your initial conditions slightly wrong, if you make a slight change to those initial conditions within a model or a simulation, then you can end up over some time scale with arbitrarily divergent outcomes, right? That's it's something that we can intuitively understand. Now, by contrast, there is also the idea of structural instability. That's dynamical instability. Structural instability is where we get the specification of the model slightly wrong. So let's say we have exactly the correct initial conditions, however those are defined, and that's another discussion, and we propagate those forward in our model, our simulation, then because the model itself is not perfectly specified, and it can never be perfectly specified, because the real world doesn't, we can't in detail specify everything, or we would have a model which is as complex as the real world. And for something like climate, something like macroeconomics, the global economy, is something to which if we were to model everything absolutely in every detail needed to get it perfectly correct, we would have something which was a duplicate of the real world, and that would leave us no closer to understanding it. So if we have this arbitrarily small model specification error, it's a mathematical result. If we have an arbitrarily small model specification error, then over some time scale, our outcomes will diverge to be arbitrarily wrong. So I call this the Hawkmoth effect, by analogy with the butterfly effect. And I think the thing to remember is that the butterfly effect is a solved problem. It's a problem of the 20th century. We know what to do with it. If we have a perfect model, then we can take an ensemble or a Monte Carlo simulation, if that's terminology that you're more familiar with. We can take a whole lot of different initial conditions around the one that we have estimated, and we can propagate that uncertainty forward within the model or the simulation, and we can come up with a range or a probability distribution of outcomes which will contain the correct answer. So the butterfly effect is a solved problem. The Hawkmoth effect is not. The Hawkmoth effect, because the initial condition space is a vector space, it can be defined in countably many dimensions, then we can specify some range of probability or uncertainty over that space. But because model function space is an uncountable space, there are infinitely many different possible things and different possible dimensions that we could add. The Hawkmoth effect isn't amenable to the same kinds of techniques to get around it. Does that make sense? So what you might say is, okay, we've got one model and we know that there's some structural instability, so let's make lots of models. And that's what we do in climate. We have models from all the different climate modelling centres. That's what we do in economics. That's what we do in many fields, is to say, all right, we've got lots of different ways of getting at this, hopefully, truth behind the scenes. We have all of these different models, and we want to use the insights of all of them to come up with some overall insight about the system. Now, we can do that. I'm not saying it's not worth doing. What I'm saying is that it's not logically coherent to use probability distributions over models as if they were a probability distribution in the real world. So supposing we have 30 IPCC climate models, suppose we have a number of models from the Bank of England forecasting interest rates, whatever, then taking those naively as perhaps kernels for a fit of a probability distribution just doesn't make sense. Okay? So that's one consequence of the Hawkmoth effect. Another consequence of the Hawkmoth effect is that model building in itself is a much more difficult endeavour than it is when you're in a nice, linear, mathematically ideal space. When you're building a complex model, you're probably incrementally adding different effects, different types of processes that you think might be happening. 3 PhD students before you went and did some nice additions to this model. It's getting bigger and bigger. It's many lines of Fortran if you're a climate modeler. I don't know what your standard 1970s era programming language is in economics. But you're incrementally adding things to something which is probably massive. And that's exactly where the Hawkmoth effect comes in again. So what we hope in this paradigm of model building is that everything we add in to make the model a better representation of reality is going to make the outputs closer to reality. It's going to make the output better. But there is no guarantee that that will happen. It's not linear. It will not necessarily, when we add epsilon x, get us epsilon closer to the correct answer. So actually that undermines model building. It doesn't totally, but it undermines the process of model building by which we expect to be able to get incrementally closer to a solution. And it undermines the process of iterative model development by which we say, okay, I'm going to add in this, it'll get slightly better, I recalibrate, I add in something else, it gets slightly better. So we must always bear this in mind, that again, we are stuck with this issue that the model world, model land, is not the real world. So that's the Hawkmoth is my dangerous beast. Fantastic objects. This is a concept introduced by David Tuckett of the Cruise Network and UCL. Some of you might be familiar with his work. I think that we can treat many statistical and analytical methods of modelling and simulation as fantastic objects. They are sort of castles in the air, if you like, of extreme rationality built around an assumption or a neglected assumption that the model world is the real world. We can go into a whole load of detail, selecting the best model, calibrating it, working out many different features of this model space. But what does it actually have to do with reality? That's the question which often goes unanswered. We can write any number of papers saying, I ran my model with these different boundary conditions and I got the following results. Great, publication, fantastic. But if we are going to assert that our models are relevant for decision makers in the real world to make decisions based on the outcomes of those models, then we have to find an exit from model land. We have to find a way to relate the outputs of those models to reality. So I'm going to say there are two ways to do that. The first is, some of you might be saying, oh, but this is ridiculous because my model is really well calibrated, I've got lots of data, I can go back and check it, and it does perform well. I have these model evaluation techniques, maybe you call them calibration, evaluation, validation, verification, and all that. There's a large literature about it. Now, if you are in a situation which we might call weather-like, if you are in a situation where you are making a forecast for a short time, and within the lifetime of your model, you expect that you'll be able to make lots of out-of-sample predictions, forecasts, and you will be able to check them against data, then we're in a really good epistemic position, in that we can then go back and say that what was the statistical reliability of this model? And if we also then assert that the conditions in the future are sufficiently similar to the conditions in the past that this assumption will probably still hold, then we can use that evaluation to tell us about the statistical reliability of our model in the future. Great, so that's the best possible outcome. Now that only applies to what I've called weather-like situations where we have this data. What if we don't have this data? So I would contrast that then with climate-like situations. And much of macroeconomic forecasting, I would argue, is in a climate-like situation. Because you're forecasting into a domain where you don't necessarily expect the underlying processes to remain the same as they were in the past, where your model was calibrated. Okay? In climate, we are clear that climate change is taking place, therefore we are not certain that all of the processes that we have calibrated our model for the 20th century, that they will work well at the end of the 21st century. I'll leave it to the audience to think about ways in which your model has the same issues. It's what's called a reference class problem. How do we know that the things that we are analysing in model land are like the thing that we are interested in predicting in the real world? So how do we find an exit there? Okay, well the answer is there is only one way out in that space, and that is making an expert judgment. Now, there's a lot of literature about expert judgments, and I don't mean it in the trivial sense of somebody going, oh well, I think it must be X, and just writing something down on a blackboard. There are essentially what we mean is, to what extent is A like B? To what extent is the model performance good enough, adequate for purpose in its simulation of the real world? We can look at lots of different aspects of this. I'll give one example and then I'll stop. The Intergovernmental Panel on Climate Change suggests that the headline predictions for the end of the 21st century for climate change are within some range, and that range is generated from a 90% confidence interval of the model output. And what the IPCC say, in their expert judgment, is that there is a 66% chance, likely in their terminology, of the real-world outcome, given that forcing, being very well defined, given that forcing, falling within that 90% model range. So essentially what they're saying is that they are reassigning a large amount of probability mass from within that model range to outside that model range without making any specification as to what the tails then look like. So I think that that's a coherent and sensible, if slightly disconcerting, way of handling that kind of model error. That's a good way to escape from model land and make a statement which, as the IPCC is attempting to inform policymakers, to make a statement which is applicable to the real world, not solely to the models that we use to generate it. So I think maybe in the discussion we could look at ways in which that applies in macroeconomics. Thank you.